Could I remove these things? So, let me just take into account L0 minus A, which 1/2 alpha 0 square plus n minus A, and this is equal to alpha prime by 4 PL25 plus alpha prime by 4 PL, let me call it nu, PL nu. Here nu goes from 0, 1, 2, 3 up to 24. You see, in the earlier one, if you recollect, mu was going from 0 to 25. But this term we separate out. Including this, there are 25. Okay, I mean 26 dimensions. And so this term we separate out. And so, if you like, alpha prime by 4 PL25 square plus. Now this if you like, alpha prime by 4 into minus m square, the mass operator. Use the mass representation. So, but this would now be, this would not include this. Okay. Earlier our m square minus m square was including p mu square. Okay, p mu into p mu, where mu was going from 0 to 25. But now it goes from 0 to 24, not along the 20. So we separate this term out, and this is okay. This is okay. And what else? I have not written the other things here, so I can write them, complete them. What was this? This was L0 minus A. So this was only this plus n minus A. If it is a open string, then only n and n minus a. If it's a closed string, then you would have nl when you have pl, okay, corresponding to alpha 0, you would have nn minus a. Okay, and analogously you can write L0 bar minus a would be alpha prime by 4 PR whole square plus alpha prime by 4 minus m square, this is okay, plus nl minus a plus nl minus, right? Is that okay? Fine, very good. So you have all these beautiful things with you, and now you can as I said, eventually we go to the limit a goes to 1. Okay, eventually we go to the limit a goes to 1, and we, as usual, we demand that L0 minus a annihilates the physical state. We also demand that L0 minus a also annihilates the physical state. So simplifying it, it would mean L0 equal to a, L0 minus a, because this is non-zero, therefore this is 0. So L0 is equal to a, and L0 bar equals to a, and this goes to 1, this goes to 1. So effectively you put L0 equal to 1 and L0 bar equals to 1, correct? You can put L0 equal to 1 and L0 bar equal to 1. And you have this here already, so you can put these things And okay, so let me remove these last lines. Okay, what we are going to do is we are going to put L0 equal to A, L0 bar equal to A. That's it. In these two equations, Okay, and then so that means we are using these equations in the our equations. So L0 minus A would then be 0, and this would L0 equal to L0 minus A equal to 0. So this would be equal to 0. Okay. So you have these two. Equations. Okay. With one with NL, one with NR. Now what you do? Once you add them and once you subtract them. Okay. Once you add them, you get an equation. Once you subtract them, subtracting is called as the level matching condition. And L0 plus, so L0, what is this? Minus 2A, of course this would hold true if I sum up the two. So that is this one equation, L0 plus L0 bar minus 2A. If I sum up those two equations, and this is non-zero, and therefore this is 0. So what I am saying is, once you add them, so you get L0 plus L0 bar equal to 2A, equal to 2. Okay, putting A equal to 1. And once you subtract them, that is called as the level matching condition. So L0 minus A minus L0 bar minus A equal to 0. So this implies that L0 minus L0 bar, this thing goes away. This is called as the level matching condition. Okay, so out of these two equations, you get these two equations. One by adding them, one by subtracting them. Okay, and that is what you do. We want to bring out clearly the dynamics played by PL25 and PR25. Okay, that is what we are trying to do, because when you add them up, they will correspond to the so-called momentum mode. When you subtract them, they will correspond to the binding mode, and then we want to see the interplay of these two. Okay, so all right, let me just, maybe I could once by adding them and once by subtracting them, we will have two results. Let me do it here. So plus NL plus NR. So I have got this equation by adding the two. Okay, this is the equation that I have got by adding the two. And once I would subtract them out, so I would get 0 equals to alpha prime by 4 into PL25 square minus PR25 square plus NL. So obviously I have got the second equation by subtracting those two equations. Correct? Very good. So now I want to define, let me write them here. I want to define two new things PL25 I want to define as NR by alpha prime plus K by R, and PR 25 as K by R minus NR by alpha. And now if I define PL25 by this, I make these two adjacent. I make these two adjacent. PL25 equal to this and PR25 equal to this. So what I do, I take the square of them. So this square plus this square plus twice of this into this. Here this square plus this square minus twice of this into this. Okay, and I want to put them back. So what I get is alpha prime m square alpha prime m square is equal to alpha prime into NR by alpha prime whole square plus K square by R square plus twice NR plus NL plus NR minus 4. And the other thing I get is 0 equals to NK plus NL minus NR, okay, which then simplifies to NR minus NL. So when in this equation, when I get NL plus NR, that means it is this equation, okay, the upper one, where I have NL plus NR. And when I have NL minus NR, I mean the difference of the two, it could be, it depends on the sign. When I take the difference of the two, then this corresponds to that. And this is what you get. You make these adjustments and then try to see what it looks like in this form. So this is what you get. And okay, let me just have a look. I want to make sure that I am not missing any important point. This is okay. This is fine. All right. So this is also good. Okay, very good. So we can then we can from here, if you sum them, PL25 plus PR25, sum these two, then minus NR by alpha prime goes away. What you get is 2K upon R, and if you subtract them, then PL25 minus PR25. So you subtract them, then this goes away and this gets added up. So this is twice n k by alpha prime. Now we are ready, we retain these results with us. If we like, we can remove these first two equations because now they are redundant. We have got these two results here. Okay. So we remove these two just to make a space for us if we want to write something more. But we retain this. What we would see that this is we want to get the physical meaning out of it. What is physically happening? This is the total center of mass momentum of the string along the 25th dimension, and this is given by 2k by r. Okay. So, and this is the difference of the two. So this is the binding mode, okay, which is related to W. Somewhere I had written W. Okay, this one half of this is W. That is how I remember. So one half of this is one half of this is W. Okay, and this is the binding mode.
Yeah, but it should be twice nr divided by alpha prime, not k.
Yeah. Wait. This was okay?
No, the bracket twice nk should be twice nr. If you subtract them.
Oh, correct. Thank you, sir. That is what you mean.
Yeah.
Correct. Thank you. That's correct. That is how it stands here also, but I am making too many slips. Okay? Is this okay? Fine? Good. Danke. Yes, but we must keep correcting, right? You please keep correcting if I make slips and mistakes here and there. Now, what we are aiming at is, we want to get the physical meaning out of these two. And how we do it? We want to consider two limits of the theory. In one limit, capital R goes to 0, then we want to see what happens to the theory. In another limit, we want to take the limit R goes to infinity. Then we want to see what happens to the theory. Okay? Interplay of R going to 0 and R going to infinity. This is what we want to see. You see, when R goes to 0, then W goes to 0, then PL25 equal to PR25. This, if you recollect, is the case corresponding to the non-compactified dimensions. For a non-compactified dimension, this is equal to this. And you find that W is going to 0, no binding. Okay? Binding mode goes to 0. This is the case when capital R goes to. Now let us consider what happens when R goes to infinity. When R goes to infinite, what happens? This guy would go to 0. Okay? When R goes to infinite, 2k by R goes to 0. This implies that PL25 is minus PR25 as well as P25, which is the sum of PL25 plus PR25, this goes to 0. So you see what happens. Let us try to see what happens in these two cases. P25 goes to 0. This also amounts to saying, which is when this is R going to infinite. R going to infinite is as good as K going to 0. Which means Kaluja-Klein excitations disappear. When this happens, what am I doing? The total center of mass momentum of the string goes to 0, which means it's no longer quantized. It becomes continuous. Okay? It becomes continuous. And when PL equal to PR 25, then there is no binding. And we know that these two modes could be physically described as the momentum modes lie on the surface of the cylinder, of course in that direction, and the binding modes they wrap around the cylinder. In one limit, so these are two extreme limits, R going to 0 and R going to infinite. So in one case you have only momentum mode survive, in one case only binding mode survive. Okay. So this is the meaning, and actually this is the let me have a look at my bars. This is the crucial point which brings us to the software called T-dualities. You want to see two theories. You map a theory which is compactified on a circle of radius R. You consider another theory which is mapped to a circle of radius, different radius, which I would now define. I define this by two things. One is R prime going to alpha prime by R, and or it is the same thing, and two and K. So these two transformations together, given by this and this, they would transform or exchange my two theories. One is compactified on a circle of radius R, and the other one is compactified on a circle of radius R prime. Okay, which are related by this transformation, which is called as the T-duality transformation. Because it was a major difficulty in the calculations in string theory, that, and this was resolved as an outcome of this. So if you do this, then in your entire, some of the expressions are still here. If you do that, you will find that the right hand side of this equation would remain unchanged under this T-duality transformation. The right hand side would remain unchanged because this and R by alpha prime would give me K square by R prime square. This would give me n R by alpha prime whole square. So the two terms will be interchanged. but this entire expression would remain the same, as you can easily see. If I write, I can even sometimes make mistake. So under these two transformations taken together, which we define as the T-duality transformation, what happens? The mask operator remains invariant. One can also see that number operator is alpha mu dagger, alpha mu. This also remains invariant. And one more thing remains invariant, and that is PL25 remains invariant, but PR25 does not remain invariant. So, under these conditions, I have taken too much space for defining this. It is enough to write this and K, and this is what we were calling as under these. So let me, if you consider somewhere, where is P25? This is PL25. This is the expression for PL25. If you substitute R equal to alpha prime by R prime here, and if you interchange K by N and N by K, okay, and R by R prime, then you will find that this remains invariant. This one does not remain invariant. This is non-invariant. So what happens under this transformation? PL25 goes to PL25, but PR25 goes to minus PR25. Okay, and this would mean alpha 0 25 remains alpha 0 25, but beta 0 25 becomes minus beta 0 25. Would become minus beta 0 25. So let me now make a space here, and because alpha 0 25 was alpha prime by 2 PL 25, and beta 0 25 was alpha prime by 2 square root PR 25. So conclusions, what happens is a state with Kn in a theory with radius r. A state with Kn in a theory with radius r is transformed into a state Nk in a theory with radius r prime. Okay, here r So we consider a theory with compactified on a circle of radius r, with this k and n gets transformed into a theory with n and k. K and n, they interchange the roles. Kn and k. And this here, r and r prime also interchange the role. And as we have seen, maybe I have removed what happens to the theories when r goes to 0 and what happens to a theory when r goes to infinity. So you find that under the duality transformation, the mass operator is preserved, so the entire theory compactified with a compactified dimension of radius r is mapped to a theory with radius r prime, okay, under a T-duality transformation, okay. And I would not derive the results for the open string. In the open string, one thing you will see is in open string theory, PL25 would be equal to PR25, so binding would be 0. There would be no binding. And it's quite physically thinkable that a closed string could bind around this circle, okay, as many number of times as it wants. The same would not be true for the open string, okay. And mathematically it looks very clear from here that these two are equal, and so this guy vanishes and there is no binding mode, so there would be only momentum modes for the open string theory. And in fact, so if you compactify an open string, okay, the binding number n would be 0, okay. And the other two things I just mentioned the results, that Neumann boundary conditions would go to Dirichlet boundary conditions, and they would go to I am not giving the proof of this because it's not 2-3 lines proof, then this will take me one more lecture. So I would prefer that at whatever point of time when you find it interesting to go further into these things, you can have a look, and then you can see this. Okay. So because I would like to, in the remaining 4 lectures, I would like to concentrate entirely on the RNS superstrings and Green-Schwarz superstrings. These are 2 different formalisms, and 4 lectures are a little bit less, but we will see. Okay, we try to see, we at least do the main important points. Okay, so RNS superstrings is one formalism. We have mentioned it couple of times in the past in our lectures. In one form you introduce supersymmetry on the bird seed. In the other one you construct a superspace and you introduce a superfield in the space-time manifold of the target space. And we try to see the equivalence of the two. Okay, under what condition, which is called as the one is on-cell version and one is the off-cell version. So off-cell version is the superspace formalism, has one extra field, gauge field into the theory, auxiliary field, and when that goes to, as a by virtue of the Oldenburg equation, when it goes to 0, this reduces to the RNS superstring. So for the spectrum, for the Fourier modes of RNS superstring and the Green-Schwarz, this would remain the same, identical. Okay, and I think I would need at least 4 lectures for that. So we might sort of conclude on this, but whenever needed, we can always come back to it. Like when we discuss the mass spectrum of the fermionic or the superstring, then of course you cannot do it without taking into account our this present Lm and Lm bar. Okay, they stay there. These alphas and betas, they stay there. They are a part of the theory, because we will simply add up the fermionic piece of the action to our bosonic, to the action of our bosonic string field. So what we have learned so far would also stay there, and it would, but we would have additional Virasoro constraints, because now we had this one equation of motion, del plus L minus x mu equal to 0, which is the Klein-Gordon equation for this fields x mu, which are the scalar fields on the worldsheet. But now on the worldsheet you also have psi mu, so you will have Dirac equations. So you will have more Virasoro constraints. We will denote them by other letters, not L, L and L bar, LM and LM bar we preserve for bosonic case, and we would have some more. Okay, we would call them by some different names, and they would be also crucial. So we look forward to that, and of course I very much love and that you people point out my slips, mistakes, errors, and please continue to do that. Okay, always correct me. Okay, thank you all very much. We can conclude for the day. Thank you very much.